Let's finally put this into action. So we have examples 16a and 16b, and I've actually added a little extra to this video as well. We have our two functions, y equals 2x squared and y equals x cubed. We already know from previous videos these two functions intersect at the points x equals 0 and x equals 2, and during that zone, during that region, 2x squared is the larger of the two functions. That's what we had that banana shape going on here. So what's happening now is we have some shapes which are growing off the board, and the idea is they're all next to each other, they're creating this solid. We want to find the volume of the solid depending on what the shape happens to be. So for 16a, the shape is going to be squares. All right. So what are we looking at? Well, according to our template there, the integral that you have to memorize, when we're dealing with squares, we have the integral from our first time they intersect, our two functions intersect at 0 and 2, so we have 0 to 2. And we want our larger function minus our smaller function. So that's going to be 2x squared minus x cubed. All right, so it's the whole thing, 2x squared minus x cubed. We want that quantity squared dx. Okay, and that formula right there is going to give us the value of the volume of the region. All right. If this was going around if it was growing with perpendicular to the y-axis. So again, instead of the squares growing this way, what if they were in the direction of this manner right here? Okay, and we kind of talked about how we can revolve around the x-axis or the y-axis or pretty much any line that we're looking for. All right. So if we're going perpendicular to the y-axis, just like before, we need our functions to be in terms of y. And so that's going to lead us towards, let me just change colors right here. We know that x will be equal to the square root of y over 2. And this one is x is equal to the cube root of y. Right? But now, on this interval, the bounds will be from 0 to 8, all right, because we're interested in the y bounds, the y coordinates, not the x coordinates. And also, the x cubed curve is now the cube root of y curve, and it is further away from the y-axis than our square root curve is. So that means it would go first. So if we were to have to do squares that were perpendicular to the y-axis, well, now our volume would be equal to the integral from 0 to 8. And it would be the cube root of y minus the square root of y over 2. That quantity is still getting squared, and our differential now, we have a very thin slice, and it's a little bit of y, so it's dy. That's the idea behind 16a, plus my little extra that I put in if it was perpendicular to the y-axis. What if it was rectangles where the height is 3 times the base? Well, it's going to be the exact same answers. We're just going to have a coefficient of 3. Again, that's all according to our template. We can figure out the area of the rectangle, and it's going to be, in essence, 3 times the quantity f minus g squared. Right? But that 3 is a coefficient, so it can go out front. So v equals 3 times the integral from 0 to 2 of the quantity 2x squared minus x cubed squared dx. That would be if the rectangles were perpendicular to the x-axis. And again, if they were perpendicular to the y-axis, same thing that we see up there. Again, we would just need the coefficient of 3 out front. All right, so cube root of y minus square root of y over 2. And we want the square of that, dy. So there's the idea of putting these volume formulas into action. Now, I will say that quite often on the exam, because these can be difficult to figure out, and they can, or maybe not as much difficult as time consuming, and we don't have a lot of time on the exam. So quite often, one of two things will happen. Either A, if this type of question occurs in the non-calculator part of the exam, they'll just ask you to set up the problem. They won't actually ask you to solve the integral. If they do ask you to solve the integral, then they may give this question in the calculator portion of the exam, so that way you can use the calculator and let the calculator figure out what this value happens to be while you're working on the next problem.